A huge disparity. Can that column carry that much weight with that much difference in size? Obviously, or they wouldn't show this picture. Yes, it does.
Yeah. I mean, I wouldn't think so, except for, you know, a couple months ago, you had that 2x4, and you said it could hold up Gabe's car.
Yeah, 2x4 can. It can hold up about 2,000 pounds. I'm sure your car doesn't weigh 2,000.
Probably not.
When you get to those columns, it's amazing how much they'll carry. In fact, I've always gotten to the point in my life where I don't ever calculate the side of a column anymore. Because there is one piece of code that states that all beams must have full bearing on their columns, which means you can't have it smaller, right? It's got to be the same width. And if you look at this, it's the same width as the beam. These things will carry many, many more times. And it has to do with the fact that that beam, until it gets long and you get torque involved, right now it's under total compression. The beam's under compression and tension. Okay, so therefore it needs much more size to carry the same weight that this does, which is only dealing with compression.
Okay, because tension, what do you mean by tension? Like it, goes,
So we went through this yesterday, the forces, tensions pulling apart, compressions pushing together. Most materials, at least our structural materials, do very well in compression. Concrete especially. Okay, so that's kind of your walls. So if you're doing a standard wall, you got a bottom plate, studs, top plate. That's what common for wood and steel. If we bring masonry walls in, such as ICFs, basement walls, which are tilted up slab, or CMU walls, then we don't have bottom and top plates unless we need to make a wood connection. Okay, they're just masonry all the way through. Roofs. Let's go to page 718. So whenever we're dealing with roofs, one of our favorite components is a truss. A truss. It's a member made of several parts that carries a load by normalizing tension and compression. Member made of several parts to normalize the load through tension and compression. In essence, it acts like a beam. A truss acts like a beam. We make trusses out of all types of materials, with the two favorite being wood and steel. Now, the way a truss works and why it just spans huge distances, so we make trusses that span easily a couple hundred feet. Okay, if we get, that's a metal truss going away. Now, if we get out past 200-300 feet, then in essence we go to something else like a suspension type where we're using cables and things of that nature. But a typical truss, how it works, you can kind of see if I take this guy, remember this is all considered one rigid structure. There's plates on the edges that hold them. So if I go ahead and put me on there, and so I kind of bow that right there. Now, you can kind of see how it works. So that board would be under compression, right? Well, what's this top part of that board under? Is it being pulled apart or is it being pushed together?
Pulled apart.
Okay, so that's under tension, right? Now this joint right here, what's it under? Is it being pulled apart or pushed together? Now it's being pushed, isn't it? Because the weight's going to travel downhill.
If it's bowed, isn't it being pulled apart from both parts?
Not in the joint. What it's really going to be doing is pushing this way, right? And so this guy's pushing back. Okay. So this guy would be in tension, that's in compression. Okay. This is going to come down, push compression here. This one, since it's being pulled that way, that goes into tension, that goes into tension, that goes into tension. So in essence, it uses every single board in here for all the weight, since they're all connected. If you put one side of the truss on compression, the other side's got to go in tension to even that out. And you just trace your way through it. You use trigonometry to actually figure this stuff out. That old law of sines, law of cosines, right angle trigonometry. So in essence, that's how we size those. Pretty ingenious device, and one that's really not been around that long. And trust, we can date back to less than 200 years ago. So that's the main type, until we get to certain distances, right? And you guys know we're spacing these on center, kind of like these pictures over here, typically 24 inches on center. Can be metal, they can be wood. Okay, so that's kind of standard where we need a good ceiling on it. We have other types where we get into big box stuff, and this, we're going to go to page 1073. Okay, so here's a different type. This one uses what we call girders and purloins. So a girder, which is this device right here, is a large beam that is nearly flat. Okay, we'll put it on a slope, like a 312, 412, something of that nature. We call that a girder. This is a girder. Now, what we've got to do to span from here to here is what we call a purloin. Okay? So that's called a purloin. And no, I don't know where those terms came from. You will also hear purloins called out there in industry. You'll hear them called girts. So you might want to think of those two terms as synonymous. Purloin and girts. G-I-R-T-S. And if you look down the picture below, that's exactly what they're calling them. So you have a girder which supports the roof. You have a purloin, which is a horizontal member to support areas between girders. And we're now doing roofs with all of the materials. Concrete's really intruding on this area. It's always been before this would be steel or wood. But now we are making, since they started developing what we call lightweight concrete, now we're starting to use concrete up here also.
So the purloin is a horizontal, the horizontal that supports the girder, or girts.
No, it supports the areas in between the girders. Okay, so these girders, what's going to, there's a floor or a roof on top of this, right? And so if snow falls on here, the purloins take that weight, they transfer it to the girder. Okay, then the girder transfers it to the edge to the column. Okay, so you always got to trace this stuff. You can't have an air gap anywhere with structural or weight. There can't be any air gaps. And so in essence, you got to pick every single spot. It's got to be supported. So if I pick this one, where's that weight going to be? It's going to be here. It's then got to go part of it to here, part of it to here. Those get transferred out, and then they go down, right? I didn't write down the page number. Let me just see if I can find it real quick. It was on a wood roof that has a rafter. See if I can find. There's a good picture of it, and I just never wrote down the page number. No. 17. Probably pretty close to there. Yeah, I probably turned to this page 1,000 times, and now that I need it, I can't get to it. Well, we do have a cross section of it. Page 715. This one's not a great picture, but when we do get into where we want more of a cathedral ceiling look, page 715. We just looked at a fairly good picture of this, but yes, we'll stick with this. This is gone. Okay, so we have our walls, and then we want this to be open space at the top. Then we have two components. Now this is typically made of wood. Okay, what you have is you have a ridge beam, which is a beam that runs all the way down the center. And then you have rafters, which go from the wall to the ridge beam. These things basically work through compression. So in essence, it takes very little to put these up. They're just plumb cut, set up there, and they're just slightly fastened. But the weight of the structure will keep it in place. So if you are doing a cathedral ceiling, you use a ridge beam and rafters. The rafters are very similar to a joist. Remember, a joist is a kind of a reoccurring horizontal device in the floor. It's kind of the same thing, but we're tilting it up on edge. And you'll have these pop up like every 24 inches or every 16 inches, or something like that. I don't know why I cannot see where that was. All of the span tables for doing those types of works, whether it's walls, joists, or rafters, is on pages 7. It starts here. Let me give you the first page number. 742 for the next 10 or 15 pages. This is a page you want to look through. If you go to page 742, if you don't know how to read a wood chart, this would be a good little section to look through. Okay? And then maybe just type it in on the internet and pull one of these up and see if you can read it. So in essence, dead load 10, dead load 20, depending on your situation, your size of your member. This one's done at 40 pounds live load. You want to make sure you're paying attention to the headers on these charts. Okay, and then how you read them. So typical most structures. We start with a footing that transfers the weight of the structure to the soil. Above the footing, we have a floor. Floors for the occupant use. Most of the time, the footing is concrete and steel. The floors can be pretty much anything. We usually don't finish a floor with steel though. Then you get to your walls. Your walls are to carry the weight of the roof. Also to protect you from the sun and wind and all that jazz. And once you get to the roof, you will have some type of beam situation, whether it is a rafter and ridge beam, or a truss, which is a single beam, or girders and purloins, if you're steel. So a few terms you might have heard before, maybe never heard. Not sure. Okay. Tomorrow we're going to dive into the concrete, all the components of our area that are concrete. What do we have on our structure that's concrete that you know of right now?
The whole day.
The whole thing? Okay, so if I'm looking at this, and I'll just look at the cross section here. So what part of concrete do we need to design? Okay, so we're going to have, now this guy right here, this is existing, right? That's the structure. So we will have this footing right here that we have to size. How many of those will we have?
6.
One underneath every column. Because in essence, what we're going to do here is when we use this concrete for this deck, we are doing a pier foundation. Right? Because I've got one column, that's a point load. So we need that. We've got a 4-inch concrete slab here. Do we really need to design that? No. Just sitting there, there's no weight on it. We do have this concrete deck right here. So we will have to haul out our steel decking and how we are going to hold that up. So we'll look at steel decking a little bit tomorrow also. Because keep in mind, we got to pour concrete up there, and we're going to have, what is that distance there? It's 10 feet, right? 10 feet from here to the edge of the deck. Okay. So how are we going to hold this up while we pour that concrete until the concrete sets? So that's what we're going to do tomorrow. Today, if you haven't finished your 2 drawings, which is this one and the one above, get those done. And then I mentioned yesterday, you only had to do half the questions for review yesterday. You can do the other half today. And we're going to get back to drawing tomorrow. Who didn't get these drawn yesterday? You two? Okay, you're going to want to have these done.
About the footings and what you wanted done.
Just estimate them for now. Well, just estimate it, just draw yourself a rectangle where it belongs. Okay. And that's all you need to do. And then once we come through, we're going to come through and do each one. Then you'll change those shapes. Okay. This is just a general configuration right now. Okay. So if you would, finish these, get your questions for review done, and then tomorrow we'll move into the concrete components. If you've got all of that done and you're good to go, then you can enjoy the rest of today, or you can jump into some Revit or whatever you wish to do. Thanks for your time. The rest of the day's yours. Please get the group together and find me a day.
Okay.